This is the Math 217 lecture on the ANOVA procedure. ANOVA stands for Analysis of Variation. It's a procedure for relating a multi-valued categorical variable to a numerical variable, or for comparing a numerical variable in more than two populations. In this way, it generalizes the two-sample mean procedure, which relates a binary variable to a numerical variable, or compares a numerical variable in two populations. So let's start with an example. So Porcine Construction Inc. wants to compare the strength of three popular building materials. So they build several structures out of each of these three materials, and they measure the force necessary to blow each one down in thousands of millihuffs. So you can treat the structures built with each material as a simple random sample of all possible structures built with that material. The data from their study is found in the 3pigs.xls file on the data page of my website. And we're going to ask the question, is this data evidence at the 1% level that there's a difference in average blowdown force of all structures built with each of these materials? Or to put it a different way, is this evidence at the 1% level that building material is associated with the blowdown force, the force necessary to blow it down? So before we look at that example in depth, let me say in general, ANOVA is going to look for evidence that the average of a numerical variable in k different populations is different. That is to say, it's looking for evidence that the means aren't all equal. So that means our null hypothesis is that the means are all equal. So if we have k different populations, mu1 equals mu2 ... equals mu k, in our case we have three populations, so we're saying mu straw equals mu sticks equals mu brick. That is to say, the average blowdown force for straw is equal to the average for sticks is equal to the average for bricks. This is what would be true if building material were unrelated to blowdown force, if knowing what it was made of didn't tell you anything about how easy it was to blow it down. The alternate hypothesis is that there's some difference among the means. And I should say that people will often write that as mu1 not equals mu2 not equals mu3 and so on. I don't like doing that because that makes it sound like the alternate hypothesis is that the means are all different, whereas in fact you could have, say, mu sticks equals mu brick, and that number is different from mu straw, then the alternate hypothesis would be true. So I will generally not write the alternate hypothesis symbolically so as to avoid that messy situation. As usual, I'll give you a quick run-through of the process, but I'll show it to you in the example, in fact in two examples, which is where it will really make sense, I think. Of course, we're going to download the ANOVA procedure from the templates page of my website. It'll be under numerical procedures with many populations, or many samples, and there will be a data tab, and we'll enter the 3 or more columns of numerical data. Since we have 3 or more populations, we will see 3 or more columns of data for the numerical variable. We'll enter that into the data tab. The next tab over is the data summary tab, and it gives the sample means and the sample standard deviations of each sample, as well as the sample size, and other information that's relevant to the computation or to checking assumptions. We'll take a look at that. The calc tab gives the p-value, as always, and as always, if the p-value is less than the significance level, we'll conclude this data is significant evidence at the alpha significance level that the categorical variable and the numerical variable are related in the population. If the p-value is greater than the significance level, we'll just say that it's not significant. Second way to say this is the data is or is not significant at the alpha significance level, that the means of the numerical variable are different among the populations straw, sticks, and bricks, or whatever your populations are. Alright, so here's a reminder of what the setup is. So we're going to go and download that data and enter it into the procedure. Let's see how that works. So here is Here is 3pigs.slx. We download it. Whoops. Fortunately, I already downloaded it. Here's 3pigs.xls. We're going to copy that data, and we are going to go back to the web page and go over to Excel templates and click on ANOVA, which is the numerical variable many populations. So third row, second column. We'll open up the ANOVA template, which will take a little bit of time. It has a data tab, a data summary tab, a calc tab, and a use tab. Here's the data tab, and as you can see, it's already got 3 data sets in here. It's got a little bit of instructions here. And it says don't use a number as a label of the column. We've seen that before, that can create problems. So we put our 3 columns of data in here. First place to go is the data summary, which tells us how big each of our samples were. We had 15 structures of straw, 16 of sticks, and 16 of bricks. It tells us our means. You see the means are quite different, right? 2.53, 3.22, and 16.35. And it tells us the sample standard deviations in each case. Down here is things involved in the calculation. You will never need to know these except if an online homework question asks for them, because they're expecting you to do those by hand. And the stuff down here, whoops, the skewness, the median, and the ratio of the standard deviations is all relevant to checking the assumptions. We'll come back to that. Here's the page that really matters. It tells us, again, the number of samples. There were 3 samples. There was a total of 47 data points. Numerator and denominator degrees of freedom are, we've seen degrees of freedom before. In this particular procedure, the statistic we use is the F statistic. The F distribution has not one number of degrees of freedom, but 2, called the numerator and the denominator degrees of freedom. And while we're looking, I'll just show you that the numerator degrees of freedom is always 1 less than the number of samples. We would write that k minus 1. The denominator degrees of freedom is always the total number of data points minus the number of samples on the nose. This is the average of everything. Here's some things involved in the calculation, and here is our F value. This F value calculates how far your X bars and S's are from what you'd expect if they were all coming from things with the same mean. And the chance of getting such a big F value is 2 times 10 to the negative 25th. It is incredibly unlikely to have happened if the null hypothesis is true. So, returning, we see our p-value, as advertised, is 2 times 10 to the negative 25th. That's less than the significance level. So this data is significant evidence at the 1% level that there's a difference in average blowdown force in all structures built with each of these 3 materials. Notice it does not tell you what the effect is. Okay? There could be all sorts of ways in which the means could differ, and for complicated, if you have many samples, that can be a complicated question. But here's one piece of, one factor. There are, in fact, more sophisticated techniques for deciding what is the effect that you're seeing, and what of all the effects that you think are significant. We will not learn those. That's beyond the scope of the course, but you can comfortably assume the dominant effect is significant. What do I mean by that? Let's show you. Excel. You can see here that the mean of bricks is very far from the mean of the other 2. In particular, it's many standard deviations away. Whereas the mean of straw and sticks, are quite close. They're maybe less than 1 standard deviation of either of them away from the other. So the big effect that you're seeing is that bricks has a higher blowdown strength than straw and sticks. Although X bar is a little bit bigger for sticks than straw, The fact that you got significant evidence you should not take as evidence that sticks is stronger than straw. The only effect that you can be confident of is that bricks is stronger than either of them. Okay, returning. What's going on under the hood? So remember, step 2 in the hypothesis testing is to assume the null hypothesis and describe a sampling distribution of some statistics. So we're assuming all the means are equal, but in fact, to get a sampling distribution, we also have to assume all the population's standard deviations are equal, and we have to assume that they all have a normal distribution. The F statistic looks at the values of x bar and s for all those samples and looks how far apart those x bars are kind of relative to s. S is, as always, your sort of unit of measurement of how far apart things are. It compares that to how far apart you would expect they would be. Typically, if you were sampling from a population where the means were all equal, this number that measures how far off these are is called the F statistic. As I said, it has 2 degrees of freedom, numerator and denominator, and it follows, if the null hypothesis is true, it would follow the F distribution, so we can calculate the probability that it's that big. ANOVA, the assumptions are a little bit more complicated. Well, the first 3 are not. The first 2 assumptions, as always, are that however many samples you have, they are all independent, simple random samples from their populations. And the second assumption, as always, is that however many samples you have, each of their respective populations is 20 times the sample size. And as always, in assumptions A and B, how many samples you view yourself as having is based on how the sample was done. If it was one big sample, there's one thing to check. Is it a simple random sample? Is the one population 20 times the sample size or more? If it was taken as 3 separate samples, or however many, then you have to check each of those separately for each of the different populations. This stands in contrast to assumption C, where you have to check the 0, 15, 40 rule for each sample regardless of how they were taken. Each of the, in this case, 3 samples, each of the K samples has to satisfy the 0, 15, 40 rule. The only difference is here, the fact that you have many samples means it's kind of a pain to check. It would be a pain to make a histogram for each of those samples. It also means that there's a certain averaging out among the samples that you can count on, which means that people tend to be much more relaxed about the 0, 15, 40 rule. In particular, if n is more than 15, this case where we would look at the histogram, instead we'll often just look at a number called the skewness. I'll show you that. The skewness measures how skewed data is, and generally a skewness of more than 1 means it's significantly right skewed, and a skewness of less than -1 means it's significantly left skewed. So we'll accept that in ANOVA as good enough. If n is more than greater than or equal to 15, then the 0, 15, 40 rule just asks that the skewness be between -1 and 1. There's another assumption. The theoretical assumption is that the population's standard deviations are all equal. Assumption D is the rule of thumb version of that, and it has 2 parts. Each sample has to have at least 5. Even if you know that the variable is normal, we're still going to assume that we're still going to require that each sample have at least 5 in it. And here's a kind of complicated one. The ratio of the largest standard deviation to the smallest must be 2 or less. That rule, I'll let you know right away, is checked on the template, so you don't have to worry too much about doing it in practice. But what it's saying is, among all the sample standard deviations, you don't want them to be too far apart, because that would be a sign that the population standard deviations are far apart. What's too far apart? Well, the biggest one is more than twice the smallest one. That's saying they're pretty far apart. The reason that each n has to be at least 5 is that if n were smaller than that, your sample standard deviations wouldn't be telling you anything useful at all about your population standard deviations. So let's check that in our example. So in our example, the simple random sample assumption, the problem said we could treat each of the 3 samples as a simple random sample of its separate population. So that's met, and that tells us that the large population assumption requires 3 separate checks. We need at least 600 structures built out of straw and 620 each out of sticks and bricks. I don't know whether that's met. That's one of the problems with using fairy tales as your examples. I will say I have a friend who has a straw bale house, so if there's 600 people like him, I guess the first one is met. 0-15-40 rule. Each sample has just over 15 or 16. So in that case, we should check the skewness. So let's do that. Oops. In the data summary page, it tells you n, 15, 16, and 16, and down here it tells you the skewness. Straw has a skewness of 0, so it's quite symmetric. Sticks has a skewness of minus 0.01. That's about as symmetric as you ever expect something to be. And bricks has a skewness of minus 0.22, very slightly left skewed. If you look at it, if you look at the histogram, you'd say, it's a little bit left skewed. But we'll consider that good enough. And assumption D needs each sample to have at least 5 in it. These are all fine. But it needs the ratio of the biggest standard deviation. So the biggest standard deviation is that of bricks at 2.87. That should be less than twice as big as the smallest, which in this case is sticks at 0.98. In fact, it is almost 3 times as large. So because this number is bigger than 2, it fails that assumption. So, returning, we see that although n is bigger than 5 in each case, the ratio is bigger than 2, so this assumption D is not met. Let's do a second example. So the file seasonfacebook.xls in the data page is a sample of college students. They were asked their favorite season and the number of Facebook friends, and perhaps you have some reason to think that, I don't know, sunny people have more Facebook friends and more likely to like summer or something like that. So we're going to ask if these 2 variables are associated at the 5% significance level. So let's go and do that test. So here is season Facebook. I'm going to, in the interest of time, I'm just going to go straight to bringing it up. Here's our data. 3 people liked winter, 6 liked spring, lots of people liked summer, and a fair number liked fall. So in this case we have 4 values of the categorical variable, what season do you like? And we're going to paste it into the ANOVA template. I'm going to click on column B and paste. So these are the 4 data sets. Here's our data summary. Average number of Facebook friends for the 3 people who liked winter is 400. For the people who like spring is 2,255. For the people who liked summer is 1,106. And for the people who liked fall is 607. Those seem like really huge differences. Like, obviously, there's going to be significant evidence that the population means are different with such big differences, but notice we have very small sample sizes, and many of the standard deviations are quite a bit larger than the mean. So there's a huge amount of variation here. Compared to the standard deviations, these aren't that far apart, as we see when we click on the Calc tab. Our p-value is now 0.152. That tells us so I guess I'm skipping ahead a little. Our null hypothesis is that the favorite season and the number of Facebook friends are independent. They're not associated, which we can write as the 4 means are equal. Our alternate hypothesis is favorite season and number of Facebook friends are associated. And our p-value, 15.2%, is bigger than the significance level of 5%, So this data is not significant evidence at the 5% level that season and number of Facebook friends are associated. Let's check the assumptions. Simple random sample? It doesn't say. All it says is it was a sample of college students. One sample. So that means all we need is that the population of college students is more than 20 times the total sample size. I guess that was 53. So we need 1,060 college students. That's easily met. 0, 15, 40 rule. We fail, right? Several of our samples had fewer than 15, maybe all of them. Let's look. Right. 2 of our samples had fewer than 15. The one that had 26 has a skewness that is way too high. Fall is the only one that looks good, but if one of the samples fails the 0, 15, 40 rule, the whole thing does. So we fail 0, 15, 40. How about assumption D? We fail that as well, because look, one of the data sets has fewer than 5, and the ratio of the standard deviations is huge, way bigger than 2. So we fail the 0, 15, 40 assumption, and we fail the standard deviation assumption. Okay, here's what you should be able to do. After watching this lecture, you should be able to state the null and alternate hypotheses for ANOVA. By now, this should be getting kind of dull. The null hypothesis is the variables are independent, and the alternate is that they are related or associated. You should be able to enter the data into the ANOVA procedure template correctly and get the p-value and state your conclusion in an English sentence. You should understand how to distinguish the dominant effect if there's significant evidence. You can't take that as significant evidence for all the differences you see among the sample means. And you should check all 4 assumptions. The 3 usual ones plus the new one about the standard deviation.